There are places in the universe where reality itself begins to break, where space folds in on itself, where time slows, stretches, and eventually loses all meaning, where the rules that govern everything we know stop working. At the center of those places lies something we still don't fully understand: black holes. For a long time, they were considered the ultimate dead ends of the cosmos, regions where matter falls in and is lost forever. But modern physics has revealed something far more unsettling. Black holes might not be endings at all. They might be doorways. To understand why, we need to begin with what a black hole really is. A black hole forms when a massive star reaches the end of its life. After burning through its fuel, the star can no longer support itself against gravity. Its core collapses inward with unimaginable force. In a fraction of a second, something incredible happens. All that mass compresses into an incredibly small point, a singularity. This is not just a dense object, it is a place where density becomes infinite, where space and time curve infinitely, and where our current understanding of physics simply breaks down. Surrounding this singularity is the event horizon. Think of it as the point of no return. Anything that crosses it, matter, energy, even light, can never escape. From the outside, it looks like the ultimate prison, but that's only part of the story. Because, according to Einstein's theory of general relativity, gravity is not just a force, it is the curvature of spacetime itself. Mass bends space, energy bends time, and under extreme conditions, that bending becomes so intense that spacetime can fold, not just curve, fold. This leads us to one of the most fascinating predictions in theoretical physics: wormholes. A wormhole is a hypothetical tunnel connecting two distant points in spacetime. Imagine taking a sheet of paper. You draw 2 points far apart. Normally, to get from one to the other, you'd have to travel across the surface. But if you fold the paper so those points touch, you can go straight through. That shortcut, that tunnel, is what a wormhole represents. And mathematically, the same equations that describe black holes also allow for these structures to exist. Now here's where things get interesting. Some solutions to Einstein's equations suggest that a black hole could be connected to something else on the other side, not empty space, not destruction, but another region of spacetime, possibly another universe. This idea is often described as an Einstein-Rosen bridge, a theoretical link between a black hole and a white hole. A white hole is essentially the reverse of a black hole. Instead of pulling matter in, it pushes matter out. Nothing can enter a white hole from the outside. Everything only comes out. If a black hole and a white hole were connected, they could form a passage. Matter falls into the black hole, travels through the tunnel, and emerges somewhere else. But if that's true, why haven't we seen anything come out? Because there's a problem. These wormholes, as predicted by general relativity, are incredibly unstable. They collapse almost instantly, before anything could pass through them. To keep a wormhole open, you would need something exotic, a form of matter with negative energy density, something that doesn't behave like anything we've ever observed in the universe. So while the math allows for it, nature might not, at least not in a way we can easily detect. But the mystery doesn't end there, because when we combine general relativity with quantum mechanics, things become even more complex. According to quantum theory, information can never be destroyed. This is a fundamental rule of physics, but black holes seem to violate it. When something falls into a black hole, all information about it appears to be lost. This contradiction is known as the black hole information paradox, and it has puzzled scientists for decades, because if information truly disappears, then one of the core principles of physics is wrong. One possible solution: the information isn't lost, it's transferred, encoded, or moved somewhere else. Some physicists propose that black holes don't destroy information at all. They transform it, store it on their surface, or potentially pass it through to another region of spacetime. In other words, what goes into a black hole might not be gone. It might just be somewhere else. There's another idea that takes this even further. It's called the holographic principle. It suggests that all the information contained within a volume of space can be described by information on its boundary. In the case of a black hole, that boundary is the event horizon. Everything that falls in could be encoded on that surface, like data on a cosmic hard drive. But what if that information is not just stored? What if it's being translated, converted into something else, something that exists beyond our observable universe? Then there's one of the most intriguing modern ideas, ER equals EPR. This concept suggests that wormholes and quantum entanglement might actually be connected, that two entangled particles could be linked by a microscopic wormhole. If that's true, it changes everything, because it means that connections between distant points in space might already exist on a fundamental level, and black holes could be the large-scale version of that same phenomenon. Now imagine this. A black hole forms in our universe, matter falls in, energy collapses, information is compressed, and instead of ending, it continues. On the other side, in another region of spacetime, that same information emerges, reconfigured, reorganized, perhaps even forming a new structure, a new environment, a new universe. Some cosmological theories even suggest that our universe could have been born from a black hole in another universe, that what we call the Big Bang might not have been the beginning of everything, but the continuation of something else, a transition from one universe to another. If that's true, then black holes are not just objects. They are processes, cosmic transformations, points where reality folds and something new begins. But there's a catch. Everything we're talking about exists at the edge of our understanding. We cannot observe inside a black hole. We cannot see beyond the event horizon. Everything we know comes from theory, mathematics, and indirect evidence. And yet, those theories are incredibly precise. They predict behavior that we've confirmed again and again. Gravitational waves, black hole mergers, time dilation near massive objects. All of it matches what Einstein predicted over a century ago. So when those same equations suggest something deeper, we pay attention, not because it's proven, but because it's possible. Black holes force us to confront a fundamental truth, that reality is not as simple as it appears, that space is not empty, that time is not constant, that the universe may be far more connected than we can perceive. And maybe the most unsettling idea of all is this. What we see as an ending might just be a transition we don't yet understand, a doorway we cannot yet cross, a boundary we cannot yet see beyond. Because if black holes really are portals, then every time a star collapses, it might not be dying, it might be opening something. And somewhere beyond everything we can observe, there could be entire realities born from what we thought was the end. If you want to uncover more mind-blowing cosmic mysteries and explore the hidden secrets of the universe, stay with us, subscribe, and join our journey through the most fascinating science discoveries.